Unit 2, the first chapter in Unit 2, and actually this is chapter number 11, is the alkali metals. Starting with alkali metals, that's actually the common name we give to group 1. So in group 1, we have lithium, sodium, potassium, rubidium, cesium, and francium. Let me tell you that out of all of these, this one is radioactive. This means that any atoms present of francium naturally would keep on decaying and would keep on converting into different other atoms. So this won't stay in the form of francium. So we're going to discuss these in a lot more detail, and we're not going to give francium a lot of effort. So starting with what's written over here, that's group 1 in periodic table, alkali metals. If we use the word metals with a group, that means all the members are metals. So all of these are metals, and there are no exceptions. Francium, bottom of the group, radioactive. One of its isotopes is produced during the radioactive decay of uranium-235, but it's extremely short-lived. At any one time, scientists estimate there are only about 20 to 30 grams of francium present in whole of Earth's crust. So no one has ever seen a piece of francium. So what we're going to do is that we're going to discuss the rest of the properties of group 1, and you're going to predict what francium would be like from those properties. So let's go on with this table. The physical properties we usually predict are melting point, boiling point, or density. In this case, what you would notice is that for melting and boiling points, what happens, unlike the whole periodic table, when you go down the group, they decrease. Both of them actually, melting point as well as boiling point. So you would see that the highest melting or boiling point is of lithium, and the lowest melting and boiling point is that of cesium. So we can easily say that going down the group from top to bottom, the melting point and the boiling points decrease. However, what happens if we go down the group? The density increases. Actually, if we talk about density for the entire periodic table, the same thing happens. Density increases from top to bottom. However, there is an anomaly, an odd behavior shown by potassium. But at this level, we do not discuss the reasons of this odd behavior. You would see this one's increasing, and then there is a decrease, and this one's increasing, so on and so forth. So we call this an anomaly. Anomaly means an odd behavior. Odd behaviors are usually discussed at higher level, but not at this one. So we're gonna straight away go with the decrease in melting point, boiling point, but increase in density from top to bottom in group 1, the alkali metals. I'm gonna clear this up. We're gonna move on to the next page. So the same things are written over here, but something extra what's written over here is this. Lithium, sodium, and potassium are all less dense than water. So it will float on them. These metals, whenever they are thrown in water, they will float on the top layer of water. These metals are also very soft. This is another property, and are easily cut with a knife. This is what soft means in terms of metals in periodic table, and they become softer moving down the group, which means if let's say I compare lithium and sodium, this would be softer. If I compare potassium and cesium, this would be softer. So that kind of comparisons have been a part of past papers, but I think they're pretty easy questions when it comes to that. They're shiny, and they're silver in color when they're freshly cut, but they tarnish very quickly upon exposure to air. Tarnish is actually reaction with oxygen. They can easily react with oxygen in the air, and they can change their color. We call this tarnishing. When the appearance of metal changes upon reaction with oxygen, we call it tarnishing. And in this case, this silver color, the shine goes away. And what happens is that it then has a dull, darker appearance. So the appearance changes with the reaction with oxygen, and we call this tarnishing. Now, among all of these changes, the changes which are further explained are given over here. Let's take a look. The reason that the melting points decrease is that the atoms get bigger as we go down the group, which means lithium has only 2 shells, sodium has 3 shells, so it's gonna get bigger. Potassium has 4 shells, so you would see that at every step down the group, they get bigger and bigger. In the metallic lattice, nuclei of positive ions are further from the delocalized electrons in cesium. This electron would be farther away in potassium, less in case of sodium, even least in case of lithium. So the delocalized electrons in cesium then in sodium, and therefore there are weaker electrostatic attraction. So that's why the melting point decreases, because the attraction between the nuclei of potassium and the outermost shell electron in potassium is different. Now comes the part of storage and handling. Why are we talking about this? Because if it can even react in air with oxygen and the appearance changes, and even if the chemical identity changes, we got to store them and handle them carefully. Which brings us to this topic. Let's take a look. All these metals are extremely reactive, and they get more reactive as you go down the group. They can react quickly with oxygen in the air, and they form oxides, for which I insist the students that you need to write the reaction and this is the balanced chemical equation of this reaction. So you would see when we're talking about oxygen, they react with oxygen and they form an oxide. There is another problem. They react rapidly with water. In that case, they form strongly alkaline solutions of metal hydroxide. So what happens, sodium reacts strongly with water. It forms sodium hydroxide, and it gives us hydrogen gas as well. So this is why group 1 metals are commonly known as the alkali metals, because they give alkaline solutions of sodium hydroxide. Now, as soon as we're going to bring them in air, they're going to react with oxygen in the air. They're going to react with water vapors in the air, as both things are present in the air all around the world. So lithium, sodium, potassium are stored under oil. We don't even store them in air. We don't store them in water. They would react and they would completely change their identity. They would either be converted from metals to oxides or from metals to hydroxides. Rubidium and cesium are so reactive that they have to be stored in steel glass tubes to stop any possibility of oxygen getting at them. Great care must be taken not to touch any of these metals with bare fingers. There could be enough sweat on your skin to give a reaction, producing a lot of heat and very corrosive metal hydroxide. And what we say is that they can eat up your skin. The common lines we write. So if they can eat up your skin, so we make sure we never touch them with bare fingers. We always use tweezers, pair of tongs, stuff like that to handle them. All right, there you go. You can see lithium, sodium, and potassium in oil. And you can see some of them are so light that they are even floating in the oil, which completes the storage and handling part. Let's talk about the family as a whole. When we talk about groups as families, we use the word because the entire groups can show you the similarities. What kind of similarities? Let's talk about that. Historically, alkali metals, historically, alkali metals were put in the same group because of the similarity in properties, before anyone knew anything about electrons. Now, there are two reasons we put these elements in group 1. First one, they have one electron in their outermost shell, something we have discussed in Unit 1 in pretty good detail. Take a look. Lithium has 2 shells, and in the last shell, it has 1 electron. Sodium has 3, the same case for the last shell. Potassium has 4, the same case for the last shell. So you would see the number of electrons in the valence shell are always same. And because of this, next point, they are going to have similar chemical properties. Remember, the reason of similar chemical properties is this kind of valence shell electron filling. For example, they're all going to react with water in the same way to form a hydroxide, for which the formula is like this, and they're going to produce hydrogen as well. They all can react with oxygen to form an oxide, the formula for which is this. They all can react with halogens to form compounds with the formula this. We usually call them salts, right? And they can form ionic compounds which contain M-positive ions, such as sodium positive and potassium positive, most of which we are familiar already. So moving on, the chemical properties depend upon the number of electrons in the outermost shell, something that I've just explained. So reason 2 is just a consequence of reason 1. Again, something in repetition, I've already said that. So let's start with reactions with water. All the metals react in the same way with water to produce a metal hydroxide and hydrogen. But that's not it, that they react in the same ways. There are no difference in the reactions. The main difference between the reactions is how quickly that happens. So 2 of the metal, they are denoting with the metal M, and then consequently, they are denoting the metal hydroxide with MOH. So the rest of the equation always remains the same. Replace this M with whichever metal you are talking about, and the entire equation would form in a similar way. Replace it with lithium, this would be lithium hydroxide. Replace this M with sodium, this would be sodium hydroxide. So it's pretty simple. So as you go down the group, the metal becomes more reactive and the reaction occurs more rapidly. So much so that, in fact, let's go with the diagram first. With sodium, in case of sodium, this is the reaction. Sodium floats and melts into a ball. Hydrogen is evolved from both sides. A white trail is formed when it's dissolved in water. This is because it's producing alkali at the same time. The ball moves rapidly around the surface because of its less density. So we need to understand that most of the time hydrogen is reacting, it is present as molten sodium and not solid sodium. Writing L for the state symbol has the potential to confuse an examiner is probably best avoided. So we still write it with an S. The main observations you can make when this reaction occurs are the sodium floats because it is less dense than water. I've already said that. Now, secondly, sodium melts into a ball because its melting point is low and a lot of heat is produced by the reaction. So this heat is enough to melt the sodium from solid to liquid state. This is fizzing because hydrogen gas is produced. Now, sodium moves around on the surface of water because hydrogen isn't given off symmetrically around the ball. The sodium is pushed around the surface of water like a hovercraft because of the releasing of hydrogen gas from different sides. The piece of sodium gets smaller and smaller and it eventually disappears. The sodium is used up in the reaction and it's converted into the alkali. If you test the solution that is formed with a universal indicator, you would see that the universal indicator goes blue, indicating an alkaline solution has been formed. The metal hydroxide is alkaline. The solution contains the OH negative ions. When you're supposed to write observations in exams, it's better to write fizzing or bubbling or effervescence rather than a gas is given off, because fizzing is something that you observe or actually see. So when you're supposed to write observations, always tend to write with the words that are a part of visual observation, which is fizzing, bubbling, or effervescence, rather than what's actually happening behind it, which is a gas is given off. Comparing other metals in the list, with sodium, lithium has this reaction. It's similar to sodium, except it's slower. Lithium's melting point is higher. Heat isn't produced so quickly, so lithium does not melt. If we compare potassium, its reaction is faster. Sorry. So potassium reactions is faster than sodium's. Enough heat is produced to ignite the hydrogen. It burns with a lilac flame. And here, lilac means something close to purple. So the reaction often ends with potassium spitting around and exploding. So you see, as we're going down the group, the reaction's becoming faster and more violent. Rubidium and cesium are even more violent, and the reaction can be explosive. Rubidium hydroxide and cesium hydroxide are formed. So you would see something I want you to notice is that they are using different adjectives. They're using slow for lithium. They're using fast for potassium in comparison to sodium. They are using violent and explosive-like words for rubidium and cesium. So you would notice that they are using 5 different adjectives for 5 different elements. This should give you an idea that you are supposed to do the same in exams too. And the same kind of hint is given over here. There are a couple of hints. Let's go through both of those. When you are asked about this in exam, you're often asked to compare the reactions of sodium and lithium. So you should explain how you can see the reaction of lithium is slower. For example, you can say that it fizzes more slowly, or lithium moves around more slowly, or it takes longer time to disappear, or lithium does not melt or is not converted into a small ball. These are the terms that you can use to state your visual observations. Again, if you're asked to compare potassium with sodium, use phrases such as fizzes more vigorously. There is another adjective he's using, or moves around more quickly, or disappears more quickly. So slower, normal, faster, vigorous, quick, violent, explosive. There are many words which you can use to your advantage comparing two metals and their reactions. Remember to use the words violent and explosive only with rubidium and cesium, because you can't use those words with potassium, sodium, or lithium. Remember to use the word slower only with lithium. In this way, you can manage your words, different words with different metals, explaining to the examiner what you have seen or how the reaction goes. Make sense?
Yes.
Good. Let's move on. Now, in case of chemistry, we need to explain the increase in reactivity. We have been consistently saying that as you go down the group, the metals become more reactive. Now, explaining those, remember, we have previously discussed the reactivity has everything to do with the valence electrons. Talking about that, in all these reactions, the metal atoms are losing electrons and forming metal ions in solution. Let me tell you, connecting it to the previous topics, this one is an oxidation reaction, as oxidation is loss of electron. So that happens to most of the reactive metals. The difference between reactions depend upon how easily the outer electron is lost in each case. Now, it depends upon how strongly it is attracted to the nucleus. Remember, we have discussed the distance between the outermost of the valence electron from the nucleus. the more the distance, the less strongly it is attracted to the nucleus. The less strongly it is attracted to the nucleus, the easier it is to lose the electrons. So, more the distance, easier it is to lose the electron. So, this is a pretty good way to go through it. Or even if you don't want to talk about this, you can simply say, because the distance is greater when the atomic size is greater. Or even if we don't discuss that, or the examiner does not discuss it, you can discuss it in another way. Now, more down in the group the element is, easier it is to lose the electron. So it's difficult to lose electron in lithium, but it's easier to lose the same in sodium. It would be even more easier for potassium or rubidium, or cesium has the easiest capability of losing that electron. So remember, the reaction was slow in case of lithium. It was fast in case of sodium. In potassium, the reaction got vigorous. In rubidium, the reaction got violent. And finally, in cesium, it got explosive. Hence, using these terms, we can easily explain the chemistry behind it. Are we good?
Sir, I have a question.
Go ahead.
When people say something loses electrons, they put, isn't it supposed to be like a plus sign, and then for when it gains a minus sign?
Yeah, so there is a plus sign over here.
No, I mean for when you wrote more down, it is in the group. At the end, you wrote E minus.
Oh, that's the charge of electron. This one is the charge of electron, just like over here. Electron has negative charge. So electron is represented with a small e, and the charge on the electron is represented with a negative. Just like proton is represented with a small p, and the charge is represented with a positive sign. Neutron is represented with a small n, and we don't write anything on top of neutron because that's neutral. Were you asking about this negative on over here and here?
Yes.
Okay. E, small e represents electron, negative represents its charge. It's the negatively charged electron that we are talking about. However, the metal ion is represented with the positive sign because now there are more protons than electrons in the metal ion. Good enough?
Yes.
Any other questions before we move any further?
No.
All right, so I'm going to clear it up and let's move to the bottom of this page. So as you move down the group, the atoms have more shells of electrons, they get bigger. So sodium atom is bigger than lithium, potassium is bigger than sodium. As the atoms get bigger, the outer electrons from which one electron is present, the valence bond, is lost even easily because it's further from the nucleus and less attractive. So electrons released by the metals are gained by water molecules producing hydroxide ions and hydrogen gas. So that's what happens over here. So finally, we are left with, if I compare both of these reactions like this, and these are the two electrons that we have used over here. Remember, there is hydrogen gas, but there are a couple of ions over here. That's why these two ions combine to form the sodium hydroxide we've been talking about. So that's how we balance these two reactions, and this and this. These are the two products of this reaction. Make sense?
Yes.
Good. Let's clear it up and move to the next page. Okay, reactions of alkali metals with the air. We are going to talk about tarnishing. Remember, these reactions are the one which we use the word tarnishing for. Right? Lithium, sodium, and potassium are all stored in oil because they react with air, actually oxygen in the air. If we look at the piece of sodium which has been taken out of oil, it usually has a crust on the outside, this kind of gray-black color. It is not shiny until it has been freshly cut. When a piece of sodium is cut, the fresh surface is shiny, but it tarnishes rapidly, which means freshly exposed sodium reacts with oxygen in the air. The same thing happens to lithium, but it tarnishes slowly. Here comes the effect of the reactivity difference. So we're talking about the same reaction, but how soon or how slow the reaction is going to happen is the difference between these metals in the same group. So lithium reacts slowly than sodium. A freshly cut piece of potassium tarnishes extremely rapidly, more quickly than sodium. In this way, we can again see that how are they going to react. Remember, in each case, the metal reacts with oxygen in the air, forms an oxide with this general formula, N2O. If we heat each of the metals in air using a Bunsen burner, we could get a much vigorous reaction, and it is more difficult to see which metal is most reactive because all the reactions are so rapid. What happens when we heat them up is that lithium burns with a red flame and it forms lithium oxide. Sodium burns with a yellow flame and forms sodium oxide. Potassium, however, burns with a lilac or purple flame to form potassium oxide. This is the general equation for these reactions. Remember, in each case, product formed is a white powder. This is only the color of the flame which we are supposed to memorize for different metals. Remember, for lithium, red; for sodium, yellow; for potassium, lilac. Remember, the charge on the oxide ion is O-2, and the charge on the alkali metal is M+. That's how we are capable of getting these charges in formulation, getting this kind of formula, this form, right? Now, there is one more thing we need to understand over here, and that's an extension work. When the alkali metals react with air, other type of oxides can also form. We may call them peroxides, the formula for which is M2O2, or superoxides, the formula for which is MO2. These all still contain the M+ ion. It is the oxygen part which is a little bit different. Remember, lithium can also form a nitride reacting with nitrogen in the air. However, other alkali metals tend not to do so. They may do so, but under specific conditions, not easily. So remember, there can be other types of oxides as well. Keep in mind, this is just an oxide. This one is named peroxide, and this one is named superoxide. So the formula changes and name changes too. Moving on, compounds of alkali metals. All group 1 metals ions are colorless. That means their compounds will be colorless or white until they're combined with a colored negative ion. Potassium dichromate is orange, for example, because the dichromate ion is orange, not because potassium is. Or potassium manganate 7 is purple because manganate 7 ion is purple, not because potassium is. Remember, group 1 compounds are typical ionic solids, are mostly soluble in water, and are white solids as they have previously discussed. We may also call them colorless solids, but white solid is a good way to say it. In exams, I appreciate students writing white solids as their state. So let's summarize all the features of group 1 elements. They are metals, they're soft, which by the way means that we can cut with them with a knife. They have low melting points, they have low densities as compared to the rest of the metals of periodic table. They have to be stored out of contact with air or water. That's why they are stored in oil. They react rapidly with air to form coatings of metal oxide. We call that tarnishing. They react with water to produce an alkaline solution of metal hydroxide and hydrogen gas. They increase in reactivity as you go down the group. They form compounds in which metal has a +1 ion, which means they lose their outermost electron. As in their village shell, they only have 1 electron. They lose that one specific electron to gain this +1 ion charge. They mainly have white or colorless compounds, which dissolve to produce colorless solutions. Now, predicting the properties of Francium. Sorry. As we move down the group in periodic table, the properties of elements change gradually. So if you know the properties of most of the elements, you would be able to predict the properties of elements we don't know yet. Francium is extremely radioactive. Predicting its properties, it's softer than any other metal in the group. It would have a melting point around room temperature. It would have a density probably just over 2 grams per cubic centimeter, higher than water, of course. It would be a very silvery metal, but will tarnish almost instantly in air. It would react explosively with water, giving francium hydroxide and hydrogen. It would even be more reactive than cesium. It would have a hydroxide for francium hydroxide with the formula FrOH, would be soluble in water and form a strongly alkaline solution. Of course, universal indicator will turn either to blue or to purple in this case of solution. Remember, it will form compounds that are white, colorless, and will dissolve in water to give colorless solutions too. We can also use a graphical method to predict the melting point of francium. If we plot the melting points of all the alkali metals against their atomic number and draw the align of best fit graph, we can easily get the value. Take a look. If atomic number increases from left to right on the x-axis of the graph, and on the y-axis, the melting point increased from 0 to 200. Remember, lithium had the highest melting point, and it went on decreasing. So this one's for lithium, this one's for sodium, this one's for potassium, this one's for rubidium, this one's for cesium. And of course, we can pick this one for francium. So if we carry on to atomic number 87, we can predict it about around 22 degrees centigrade. But there are other various predictions which give a melting point of francium between 21 to anything around 27. This is just one easy way of predicting it. We have more scientific, more complicated, sophisticated methods to predict the melting point of francium. Hence the values ranging from 21 to 27 degrees centigrade. Moving on, I think we're done with the chapter. Yeah, we are done with the chapter.